Hi, everyone. I'm Dan Parker, and I'd like to thank the organizers for inviting me. I'm very excited to tell you all today about how crystallization can create Chern insulators. So I want to tell you today about how we can understand some of the lovely fractionalized physics we've been seeing in Moiré bands and zero magnetic field. I'll start by talking about the idea of vortexable bands and how I believe they can really inform the physics in twisted MOTE2. And then I'll go on to the wilder case of pentalayer graphene and talk about the idea of the anomalous Hall crystal. Before I get going, I'd like to begin by thanking the team. This has been a collaboration between some folks I know at Harvard and at Berkeley. And I'd especially like to highlight the contributions of Taiga Wang and Chenle Wang, who are two lovely grad students who are going to be on the postdoc market this year. Okay. Yes. And also Patrick. Yes. Oh, right. Yes. Okay. Yes. Patrick is also on the job market this year. I forgot. All right. So as I mentioned, our inspiration today is the lovely experiments from Xiaodong's group and many others now, and also Longzhu's group on both twisted MOTE2 and pentalayer graphene. So both of these are what I would call phenomenal realizations of fractional Chern insulators or fractional quantum anomalous Hall physics at zero magnetic field. And I want to start by saying some sufficient conditions we know theoretically for this physics to appear. It was known basically from the outset that you need an isolated band for fractionalized physics to appear, so the interactions can be very strong and play a crucial role. And you also need a Chern band so that you have topology in the mix to mimic Landau level physics. But this alone cannot be enough, because we know that in the 50th Landau level of gallium arsenide, it's a flat Chern band, but experimentally you don't see any fractionalized phases appearing there. So there must be a missing ingredient. And over the last few years, drawing on a very long line of work started by Rahul Roy and others, we now know that the missing ingredient is this idea of ideal or vortexable bands. So let me tell you very briefly about what a vortexable band is. A vortexable band is a band where if you shine right circularly polarized light on it, you will see no interband excitations. Or in more mathematical terms, if you take a vortexable band and multiply by z, x plus iy, then you will get another wave function within the same band subspace. So this property is, it turns out, what you need to mimic the lowest Landau level in a very crucial respect. And one just sort of example of why that's good is you can go and do the following construction. If you start with a vortexable band, it's also a flat Chern band, you can write down a generalized Laughlin wave function, and under reasonable conditions, this will be the exact many-body ground state. So if you have a vortexable band, a Chern1 vortexable band, this will allow you to have a direct analog to the lowest Landau level with all of the Laughlin and Jane and other fractionalized physics that that normally has. I want to note, though, that vortexable bands are an idea that extends beyond the lowest Landau level. You can have vortexable bands with any Chern number 50. You could have vortexable bands that are higher vortexable bands analogous to the first Landau level instead. And we have a paper on that now. So with vortexable bands, we can write down three sufficient criterion, not necessary, but sufficient criterion for a band to display the same physics as the lowest Landau level. So what I want to do is take these criteria and apply them to the case of twisted MOTE2. There we select a standard model following ab initio parameters from Deschaux, and you get a nice isolated Chern band. It's not especially flat, but once you dope to filling -1, it flattens out very, very nicely. It's a Chern band, as you can see from the Berry curvature. And when you compute the trace condition, which will tell you how close you are to being vortexable in this case, then you can see that it is the failure of vortexability, which I'm plotting here, is at most 0.2, which you should compare to 1. And so this is very small. This is very close to the ideal limit. And so based on these three criteria being satisfied, we expect lowest Landau level physics to appear. And, you know, this is post-dicting the experiment, so it's no surprise that from that perspective, fractional Chern insulators were seen. But where I want to go with this is one step further, which is to go to half filling. Half filling of the lowest Landau level is a very special place where the composite Fermi liquid is thought to be. This is a very unusual state, first proposed by Halperin, Lee, and Reed in 1993. And it is a non-Fermi liquid composed of composite fermions, which you can think of as an electron bound to two flux quanta. Since they are charge neutral, even though they form a metal, that is a very unusual metal without any electronic Fermi surface. But if you were to look at neutral excitations, you would still see gapless neutral excitations from densities scattering across the Fermi surface. So this has been experimentally tested in the lowest Landau level in the 90s through various experiments. And there's a whole host of theoretical work on it. So what we wanted to do is look and see if this is going to be there as well in twisted MOTE2. To do this, we went to numerics, and we used tensor network methods, DMRG, so that we could go to very, very large sizes. And here on the right, I'm showing you what the electronic occupations look like at half filling of that Chern band. So here, I'm showing what happens under very, very weak interactions. And here I'm showing what happens at realistic interactions. On the left, you can see that there is a clear Fermi surface. We get a Fermi liquid. And on the right, there's no particular feature at the place where you would expect a Fermi surface. So here we see almost uniform occupations. Yes.
Interaction? Are you using a model short-range interaction, or is it Coulomb interaction?
It is screen-Coulomb interactions with epsilon r equals 8.
Screening not from the electrons, from the
HBN, yeah.
So it's tangent hyperbolic function.
Standard, yeah. Yeah. That was,
Yeah,
yeah. Yeah. Good. Okay. Then to probe for, so we're expecting though that there's still a hidden Fermi surface there, just not visible from the occupations. So for that, we want to look at the gapless zero charge response of the system. And so I computed the static structure factor, which I display here. Now both sides look similar. The Fermi liquid and the putative composite Fermi liquid both have structure all the way out to 2kF, as you would expect from a Fermi surface. And to really nail that down, here I'm resolving that plot into line cuts. And you can see that there are peaks in the structure factor corresponding to every momentum scattering across the Fermi surface. So putting these together, we see that we have both numerical signatures we would expect of a composite Fermi liquid, absence of a Fermi surface in the electronic degrees of freedom, but still every signature of a Fermi surface in the neutral degrees of freedom. So numerically, we can conclude that there should be an anomalous composite Fermi liquid in MOT2 at half filling. And in the experiment that came out after our work, we see signatures consistent with that. we see the right Hall conductivity going through exactly 2h over e squared at half filling, or, almost exactly. That would be what we would expect from a composite Fermi liquid at zero magnetic field. So in the future, I'm hoping that perhaps there can be some direct signatures of this from cyclotron resonance or surface acoustic waves or other techniques like that. Okay, so I think this is what I would call a success story. We can understand many of the non-trivial workings of twisted MOTE2 from ideas of vortexability and quantum geometry and our many-body apparatus. The situation in pentalayer graphene is much more puzzling, however. There, just looking at the experiment, there's a couple of things that seem very odd. First of all, the experimental phase diagram is highly asymmetric between displacement field up and displacement field down. And because of that, it's very unclear what the Chern band might be coming from at all. The electrons, where you see the Chern band in the fractionalized physics, the electrons are pushed to one side of the system, the side opposite to where the Moiré is. And so because of that, it seems, at least in, at face value, that the Moiré might not be very important. If you think about the strength of the Moiré in straightforward modeling, then you find that it's very, very weak, on the order of 0.3 MeV, compared to tens of MeV in TMDs or about 100 in graphene. So if we go to our three criteria, try to get a handle on the situation, we find that we don't even have a gapped band to start with. You can't even check if it's a Chern band because you don't know what band to work with. And, forget about the geometry. So the situation here really was quite puzzling when we first saw this. And because of that, we opted to take a rather phenomenological approach. Right? It seems that something very odd is going on here, and so we should be a little bit broad-minded. So here's the strategy. We decided to write down a simple model and really look very broadly and understand the menu of possible options that could arise. Then from those, from that smorgasbord, distill what are the universal features, what are the things that survive beyond, small details that aren't fine-tuned. And those are the things we might expect to actually see in the experiments. So that's the sort of approach I want to walk you through. And so the model we're taking very concretely is a standard type binding model for rhombohedral graphene from, I neglected a citation. It is from Jung and McDonald, plus a Moiré, a very weak Moiré on just the first layer of the rhombohedral graphene from Moon and Koshino, and then a vertical electric field. And to that, we will add screen Coulomb interactions screened by the HBN as per usual. I want to note for a second all the ways this is not realistic, right? We have no disorder, we have no temperature, we're going to assume spin and valley polarization, which you can check is reasonable. You're sort of expected to be deep within this quarter metal regime. And probably most important, in this modeling, we're assuming the Moiré is going to be quite weak or even vanishing. Okay. Aside from that, there's a couple of technical restrictions. Okay, and here's what we get. If we take this model and do self-consistent mean field at filling 1, we will see that a Chern band splits out. You split off one band from this gapless complex and get a very, very flat Chern band, which I've highlighted here in red. Here's its Berry curvature. You can see it's pretty non-uniform, that there's very little Berry curvature in the middle, and there's a lot of Berry curvature near the outside, especially at K, or kappa, the less a kappa prime. And then finally in the upper right, I'm showing the charge distribution through several unit cells. You can see that there's a hexagonal lattice here. And also, the charge density is quite far from localized. You're not localizing the charge on a lattice. It's instead spread throughout the system. Great. Okay. Let's see. I should note that these figures are as close as we can guess to the realistic experimental parameters in terms of angle and displacement field. Okay. And broadening our parameters a little bit, if we tune the angle and tune the displacement field, we see that this Chern band is part of a larger phase of Chern insulators that extends through the system and competes at very low angle with a Chern 0 insulator, which I'm calling here a Wigner-like insulator on account of its charge density pattern, which is localized to a triangular lattice. The other phase, the Chern insulator, I'll call the AHC, a name whose origin I'll explain in a moment. And in keeping with our idea that we should be searching for universal physics here, we basically tuned every parameter we could think of, and in the face of all of these, this phase survives. For instance, it's very unclear what the right Fermi velocity to consider is here, so we changed the in-plane hopping by 500 MeV, and we find that the phase diagram shifts a little, but the phases survive. We can change the interaction strength by a large factor, and the Chern insulator survives. We can change the number of layers, and the Chern insulator survives. And finally, we can tune the Moiré strength, which was already weak. We can turn it off, and we still have this Chern insulator there. I'll return to that point by and by. So because this phase is there basically no matter what you do, it seems like a good candidate for something that could appear in the experiment, something that should be pretty robust in the face of disorder and whatever else is there in real life. The only thing, as an aside, that is going to ruin the robustness of this phase is actually numerical issues. You have to use very, very careful numerics to get this to come out right, and you need very large sizes. You need a very large number of bands. And the reason for this is that you have no good low-energy subspace to do numerics. You have this spaghetti of bands, all these crossed bands going up and up and up and up, none of them separated out. And so you need a very large number of bands, at least 7 in practice, and you need extremely good resolution through the Brillouin zone to get the energies to work out to even 1%. 1% is a good marker because that's approximately the scale on which different phases compete. So in the face of this, I think it's a real challenge for the community to do reliable many-body numerics that aren't going to be strongly biased by some of these effects. As a first paper on this, we did what we could. So we did a very uncontrolled approximation, just projecting into that lowest Chern band and fractionally filling that. So we can look at that in exact diagonalization, and we see all the usual fractional suspects appear with nice many-body Chern numbers and so on and so forth. But I want to point out that, so 2/3, 3/5, 4/7, etc., they're all there. Even some of the ones that aren't there in the experiment, because we're assuming you're doping into this unchanging Chern band subspace. And you have very strong finite size effects. It's not really possible to tell what the many-body gap is because it's much more dependent on what system size you take than, where your points are in the Brillouin zone than what your system size is. It really matters if you exactly hit the K point or not, for instance. We can also do DMRG and find again, within this uncontrolled approximation, you get fractional Chern insulators. But since we don't know, right? Since our Hamiltonian starting point isn't right. There's more work to be done here to make something conclusive. So because of that, let's go back to what we do think is robust here, which is this Chern insulating phase. I mentioned a minute ago that this should survive all the way down to 0 Moiré strength. And when we think about it from that perspective, something very funny is happening here. I'm saying that interactions will spontaneously break the continuous translation symmetry we have in our model down to discrete translation symmetry, opening up a gap to give us an insulator. So this is reminiscent of what happens in a Wigner crystal, where translation is spontaneously broken, except now we are spontaneously breaking time reversal as well to give us a Chern insulator. This harkens back to an idea of Tsanovich, Axel and Halperin in '86 called the Hall crystal. And so because we are spontaneously breaking time reversal, we are calling our phase the anomalous Hall crystal. Now, to be clear, this is only a naming that strictly makes sense in the absence of Moiré, where you're really breaking translation spontaneously, but we have been labeling this Chern insulator that way throughout the phase diagram. So to actually have such a phase arise, you need very strong interactions. But let's put that problem aside for a second and think about what sets the Chern number. So let's assume for a second that interactions are very strong and are going to open up a gap. In that case, are we going to get a Wigner crystal or a Hall crystal, an anomalous Hall crystal? So to understand that, I want to note that there are two sources of Berry curvature. There's the Berry curvature inherent to the band, to start off with. We are dealing with a band minimum here, right? We've started with pentalayer graphene or similar and applied a displacement field, opening up a gap. So at the band minimum, you'll have a lot of Berry curvature, which I've denoted with this circulation here to make you think about it having, angular momentum. So that's there at the single particle level. Once you open up a gap, then just as adding a mass to a Dirac cone can give you a lot of Berry curvature, opening up the gap here can also give you additional Berry curvature. So we now have two sources of Berry curvature: the Berry curvature inherent to the band and the Berry curvature from the gap opening. And depending on which way the gap opens, those could either be the same or opposite Berry curvatures. So if they're opposite, they can cancel out, giving you Chern 0. Oops. No, where'd my... They can cancel out, giving you Chern 0. Or they can add, giving you Chern 1. And this competition can be addressed in a simple model that we've worked through, the 3-patch model, where you can come up with an analytic solution in a very simplified case that tells you, is the Berry curvature more likely to add or cancel? And what we find is that there's a relatively nice progression here. At very low densities, they tend to cancel and give a Wigner crystal. At higher densities, they tend to add and give the anomalous Hall crystal. And beyond that, you usually find a metal. So that's what I'm showing in this phase diagram down here. It's a function of electronic density versus displacement field. So because of this, it seems not unreasonable that this anomalous Hall crystal could be there experimentally in Moiré-less samples, in which case you would expect to see quantized Hall resistivity over an extended range of density. And to really nail this down, I think local probes probably would be necessary. You should look at STM or something like that and look for things like a delocalized or non-localized charge density pattern, such as I've shown here, As Yahui mentioned yesterday, you might also get some, instead of hexagonal lattices, there's probably other options depending on details, but not localized like a Wigner crystal. And there'll also be a couple of other features like periodic current loops. Okay, so let me then conclude. It's a little bit early, I guess. We have seen that at least at mean field level, and unless I specifically said otherwise, everything here has been a mean field level, that rhombohedral graphene easily crystallizes, that there is a tendency towards crystallization because of the very flat band minimum and the very large amount of Berry curvature present in the system. So depending on the density, this can give either a trivial Wigner crystal or a topological anomalous Hall crystal. And any Moiré potential you have should pin that crystal so that you fix what density it's at, fix how large the crystal is. And if that potential is big enough, you could then dope into that stable Chern band. So we don't know yet how big the Moiré potential is in the realistic system. It would be really good to have better modeling going forwards, and I think that will be a great topic and a very hard topic. And at the same time, it would be really good to have better many-body numerics for this situation. But as I mentioned earlier, this is an inherently difficult situation where you have many, many bands, and you are extremely sensitive to finite size effects, much more than in some of these other Moiré systems we've been thinking about. And so I think that's, as I said, a good challenge for us as a community. Okay. Finally, I'd like to just add there's this tantalizing hope that perhaps this might be visible in experiments without the Moiré. Thank you so much for your attention.
Yeah, my question is about the very beginning of it, this vortex stability condition. So in regular fractional quantum Hall, which you know is a very long literature, we have a very good understanding of the occurrence or not of fractional quantum Hall effect in terms of these Halden pseudopotentials. It's a very...
Wait, in terms of which?
In terms of Halden pseudopotentials, okay?
Good.
It's
yes.
a very developed field quantitatively, and basically ratio of the Halden pseudopotential decide everything. It's very well understood 20 years ago. Is there a connection between vortex stability and Halden pseudopotential, and if so, what it is, or is it something that we should figure out?
Yes. So when I say for short-range interactions here, what I mean is for V1 pseudopotentials. So maybe more broadly,
yes,
the vortexability condition is in some ways the minimal condition you need on a band for the Haldane pseudopotential arguments to go through.
Okay, so then I'm going to ask something which I'm then confused. So why do we then need a new term, vortexable? Why can't we just say it's V1? I'm confused about something then. I mean, because it's a very established literature. There must be a reason that you're introducing a new terminology, right?
Right. So Haldane pseudopotentials are interactions. This is a condition on the single particle physics before any interactions come into the mix. It's a condition that says when you add interactions, what will happen and how do you get control?
This is maybe, I'm sure you totally understand it. This is a misconception that interaction decides fractional quantum Hall effect because there are matrix elements. We know, for example, if you make a two-dimensional system wide, things change. If the Landau levels couples have things in. It's a complete incorrect statement outside the experts. That's a pure interaction thing. It's not a pure interaction thing. The matrix elements depend on all the details of single particle state there also. And in fact, there are many examples, you can change parabolic. So in that sense, is it that different here also? You are talking about matrix elements in the end, right?
Yes. So one way to think about this is that this is going to give very specific forms to the matrix elements. Okay, it's going to constrain the matrix elements in just such a way that everything goes through.
So the vortexability condition then makes things much more precise than what I could work out using pseudopotential, using my knowledge. This is very precise and very easy to test. Okay, I get it. I thought it's something like that.
I have another question about vortexability. So if you look at the flat band in twisted bilayer graphene, we know that you can map it onto an n equals 0 lambda level. Is that vortexable or not?
At the chiral limit, it is exactly vortexable. And in fact, going back historically, this is sort of how vortexability was found. Patrick Ledwith and others had a paper in 2020 which wrote down this same Laughlin-like state I have here in the lowest, in the chiral limit of TBG, and showed that you get exact fractional Chern insulators there. And then later, Jia Wang and others generalized that to the setting of ideal bands and showed that this gives numerically exact zero modes at the many-body level.
So just a question about where this Chern band lives. So in rhombohedral graphene, I think of the wave function as living on the top and bottom layer. And so this particular Chern band lives on the top layer?
Yes. So in this geometry, I've shown the effect of the displacement field to polarize all the electrons to the top.
Okay.
You can think of this like an SSH chain, where you've got a low energy topological mode pinned to one side, and those will be the conduction bands, and the topological mode on the other side will be the valence bands.
Thanks.
So I have a slightly technical question related to the composite Fermi liquid part. So if you are working with IDMRG with size 8, you showed like more than 8 cuts or KY cuts. Like how do you get those? The previous slide maybe?
Yeah, it's the same.
The same thing? Okay.
Yes. So that's because of the shape of the Brillouin zone. We are actually taking a rectangular Brillouin zone, and let's see, I can't quite reach, but there are more than 8 cuts through the largest part of the hexagon, but you can see there's less than 8 cuts on, from here to the top of the hexagons,
okay,
and
thanks.
in the middle, it's a geometry issue. Yeah. Oh, great. Yes. So with this, yeah. So this here's our lowest cut, and then this here is our highest cut, and then after that the pattern repeats with a shift.
Thanks for the really clear talk. Sorry if I missed this, but could you tell me a bit about what you saw when you had a large opposite D field where in the experiment they didn't really see anything?
Yeah. Let me show an extra slide for that. Yeah. So so here's the experiment first. So the experiment, thank you for the pointer, shows the fractionalized states are all up here off the data. And then down here on the opposite displacement field side, when the electrons are polarized next to the Moiré, you see this sequence of correlated insulators. So if we do Hartree-Fock at filling 4, using all species, then we will see, let's see, so here negative energies correspond to metals and positive correspond to correlated insulators. So we see at large and negative displacement fields correlated insulator, and at large and positive displacement fields a metal. And in the middle we have systematic effects, so ignore the gray region. Yes, so it was actually by these calculations that we know we got the orientation right. It was a question for a while, maybe we just got the sign of the displacement wrong, but it really works out like this. Yes.
Okay. So I think in the end of the talk, you made a passing comment saying at a lower density or higher density, you get either trivial Wigner crystal or metal. So is that a model-dependent statement, or is that generally true? Could you say a little bit, maybe full insight on that?
Let me pull up the slide. I have no evidence it's true beyond being a model-dependent statement at this point. Maybe let me say something vague and suggestive, that normally one thinks about the competition between Fermi liquids and Wigner crystals as being competition between position and momentum, which don't commute and are therefore frustrated. Here, however, we're adding topology into the mix so that position no longer commutes with itself, and there's additional frustration in the system. So that suggests that the energetics and the competition probably are not the same as what we're used to exactly with traditional Wigner crystal to Fermi liquids. And how that's modified would be very interesting to understand.
Thanks.
Yeah, so in Longju's experiment, as we all saw, when he cooled it down, it went to this integer state. So can you comment on this based on your theory? I know this is all zero temperature, but...
I think we still have to I think the dust has to settle a little bit more. It is facially, you are getting an extended regime with quantized sigma xy, but this is an aligned sample, and so I would have thought that Moiré might prohibit that. It also seems very strange just as a transition that there's so much of an entropy difference there. So I really am wondering if there's some sort of systematic effect polluting this. I don't want to declare victory or anything like that. Local probes would be great.
Can you put up the nice sketch you had of your three-patch model and the reconstruction? Just had a question. So you draw this picture of, adding and subtracting sources, but when you open a gap, while you add and subtract that, you make it look like you can continuously add and subtract things, but the minute you open a gap and break translation, the sum of those has to be an integer, right? It can't be. So is there some kind of locking thing that you see when you do this stuff, where you track C equals 1 numerically when you do these patch models? Because it can't, continuously change.
Yes, yes. So let me go to a little bit more detail on the three-patch model. So here's a little bit more detail on our minimal three-patch model, and let me just say a few things about it and then get to your question. So we observed that phenomenologically, the orbital spinors are very consistent in large patches of the Brillouin zone, and those patches are centered at the same high symmetry points that will determine the Chern number. So based on that, it seems very reasonable to restrict to just those high symmetry points and solve the minimal model with exactly three momenta. Throw out, 99% of the Brillouin zone. Though, of course, actually, it's, you're only throwing out a small portion of the Brillouin zone once you take that consistency into account. There, we find that two Pancharatnam phases that talk about kappa to kappa and kappa to kappa prime scattering control the Hartree and the Fock energies, and those tell you which Chern number is going to pop out. They tell you about the competition between Chern 1, Chern 0, and Chern -1, mod 3. And you can write this phase diagram thinking about what happens as a function of density and where do you end up. Here, we're showing the possible phases that result with the Fock energy or the Hartree energy competing along here. And when they fail to compete, when they agree instead, then that suggests that you really should get that phase. So this is also going back to the earlier question about why we're thinking about higher densities favoring Chern 1. In these models, at least, this picture somewhat explains why. So, yeah, have I answered your question? Maybe, yeah, okay, yeah. Yeah, okay, we can talk later. Yeah, there's more parts to it.
So generally in these systems or more broadly, what do you think is the relationship between situations that favor Hall crystals versus situations that favor superconductivity?
Well, until last week, I would have said that if you only fill a single flavor and have Valley polarization, then you should clearly disfavor superconductivity. Now I'm not sure what to think. But I think that's that should be a very interesting question going forwards, and seeing if you can see them in the same regime, if even the anomalous Hall physics and the Berry curvature there could be somehow driving superconductivity would be a very interesting question.
Thanks. Yeah, very nice talk. I would like to ask one question about this three-patch model. So if the Chern number is 1, then basically around this three high symmetry point, we can pretty much detect whether Chern number is 0 or 1. But for momentum points thrown away in this three-patch model, in case there is a band closing, gap closing and reopen, Chern number can change by 3, etc. Right? But because this is multi-layer nature, it's possible to have competing state with higher Chern bands. So it is here the assumption of the Chern number must be between 0 and 1. So we're using this three-patch model, or there is some way to deal with the possibility where Chern number, higher Chern number bands should not appear here.
Yeah, thanks. So here we are limited to Chern number mod 3 because we're considering the symmetry indicators picture of the Chern number. Let's see, this was very similar to the lovely generalization of this idea from Jennifer Cano in the previous talk. And what we can, right, so you're absolutely right that we ignore the possibility of Chern 4, Chern 37. What we can do, though, is we can solve this minimal model and then go and check in Hartree-Fock with all the Brillouin zone and all the bands. And there we find that we only get Chern 0, Chern 1, or a metal. And I've drawn the transition here in this dashed purple where we would expect the crossover from 0 to 1 in the three-patch model. And you can see it pretty well matches the large-scale Hartree-Fock.
I see. Yes. Great. Okay, if not, thank Dan again.